Star Trek notoriously plays with hypothetical ideas in physics, especially when it comes to traversing intergalactic distances. Warp drive, wormhole, can you tell us about what Star Trek gets right and wrong?
Yeah, what's amazing about those things, and when I wrote the book, what surprised me is those are among the most sort of fantastical things in Star Trek, the kind of things that seem the farthest out. And what is amazing is that they're not impossible. At least we can't say that they're impossible. I mean, the motivation is clear. Traveling at the speed of light doesn't get you very far. The distance between here and the center of the galaxy is maybe 30,000 light years, so even traveling at the speed of light, it takes you 30,000 years to get to the center of the galaxy. That does not make for an exciting episode. And so they had to figure some way to go faster than light. But the problem is that you all learn in school, in kindergarten, that you can't travel faster than the speed of light. That's what Einstein says, right? But you have to be like a lawyer and parse it a little more carefully. You can't travel through space faster than the speed of light, but space can do whatever the heck it wants. And so in fact, had Einstein been around, he would have thought of something that he would have called warp drive. And warp drive, of course, is a way to go faster than light. And the writers, of course, if you read how it's supposed to happen, of course, it's nonsense. But in fact, in principle, you might be able to do it. In fact, given the laws of general relativity, you, in principle, could, because what general relativity tells us is that space is dynamical. It can expand, it can contract in the presence of it. It can warp. And in fact, of course, I brought a few warp drives here, as you can see. We actually experimented beforehand with several balloons, but happily, the World Science Festival was able to provide another thing which works better.
Safe science.
So, yeah, safe science. In fact, always perform safe science on stage. But this is, you won't be able to see all the details. This is kind of an impressionistic example, but it actually is exactly what warp drive would be if you could make a warp drive. So what I've done here is you can sort of see the sun and the moon and Saturn, just to give you the local environment. And this is a beautiful rendition of the USS Enterprise. You would recognize that. And so I've taped it to this balloon. And here's a star system here, and here's another star system here. And I want to show you how the Enterprise can move away from this star system and towards this star system without ever moving with respect to its local surroundings. And you do that simply by expanding space behind the spacecraft and contracting it in front. So I'm just going to stand behind you. May. That's why I want to stand behind you.
Why are you doing it near me?
No, it won't. There we go. There we go. If I'd used the balloon, it would have popped. But what you can see is I squished the balloon behind it, and these stars get dragged away. But the Enterprise, of course, never moves with respect to its local surroundings. So this is possible in principle in the real universe. The question is it possible in practice? And the answer is we don't know. It's an open question. Because in order to make space expand, you have to fill it up with a very special kind of energy, something called negative energy, which sounds like something that was invented by a physicist in a room without windows for too long, which is true, in fact. But it actually exists. Due to the laws of quantum mechanics, negative energy configurations can exist for very short times, but what we don't know, and really this is the open question, is could you make enough negative energy to actually do anything like this? And we just don't know the answer. People like me actually get paid to worry about that. But the answer is if you could make negative energy configurations in principle, you could make a warp drive.
But it turns out that warp drive is more than just a science fiction fantasy. And here's why. This short equation may turn out to be a most extraordinary discovery. It might be our passport to the universe. And this is the sci-fi fan who came up with the idea when he was a college student.
I was watching Star Trek one evening, and I was on my PhD.
Trekkie, yeah?
Yeah, exactly. And in Star Trek, they always talk about warping space and relativity, and I thought maybe there should be a way in which we can do this consistently within relativity and not just talk about it. So I went back to the office, and then I spent all Saturday in the office doing calculations, and I did come up with a model, with an idea in which you can do a warping of space-time that allows you to travel faster than light without violating any of the principles of relativity.
Alcubierre's college professor was so impressed, he advised him to publish it.
I've never published a paper before in my life, so he actually had to help me to write the paper and all through the process of how you actually submit it to a journal, and it was published.
Alcubierre's equation shows it's possible to warp space and time and leap across the universe in moments. Here Here at the Multiverse exhibition in Washington, D.C., this travelator helps us understand how warping space-time can get us across the universe without accelerating.
The empty space behind your starship expands rapidly, pushing you in the forward direction. In the same way for this walkway, new space constantly emerges, which moves you along in that direction.
At the other end of the travelator, we get a sense of what's happening in front of my starship.
Space is compressed. In the same way in this walkway, space is being compressed, which moves you along. So you have the illusion that you're moving. Actually, it's space which is pushing and pulling you along.
To turn Alcubierre's equation into reality, I would need huge amounts of energy that would create a kind of bubble capable of warping space-time. At the front of the bubble, the space-time between me and my destination is compressed, pulling us together. At the same time, space-time behind the bubble is expanded, pushing me forwards. And all this happens in an instant, many times faster than the speed of light.
Miguel's warp drive is an ingenious way around Einstein's cosmic speed limit. But it's still theoretical and lacks one crucial ingredient: an exotic substance called negative energy, something that many scientists aren't even sure exists. But one man does believe in negative energy. He even claims he's created it in his lab.
The warp drive. It sounds like science fiction. But the idea of surfing across the universe in a warping bubble of space would make perfect sense to Einstein. There is one snag. A warp drive can only function with a mysterious power source, negative energy. And today, most scientists believe negative energy is just an unproven theoretical concept.
But Steve Lamoureux, an atomic physicist at Yale University, has made it his mission to track down this exotic form of energy. And he believes the answer is all around us, in the fabric of space itself.
We normally think of the vacuum of space as being as completely empty, but in fact, there's energy density in empty space, and we call that the zero-point energy of space.
The theory of quantum mechanics predicts that empty space is actually constantly shimmering with microscopic pulses of energy as particles pop in and out of existence. To make negative energy, you have to find a way to suppress this constant chatter. Steve realized the way to do this was to change the shape of space.
There's a nice analogy. If you have two ships on a rough ocean, one ship will tend to reflect waves from it, the other one does the same thing. So the wave density between the two ships is a little bit less compared to one by itself, which is surrounded by a rough sea. So you put two ships on a rough sea, they'll be mutually attracted and they'll come together.
Steve reasoned that if he created a narrow enough region of empty space like the area between the two ships, then some of the shimmering zero-point energy would not fit inside it. The energy of empty space outside the narrow region would be stronger and force it to shrink. That force would be the signature of negative energy. And Steve set out to create it in his lab. It was an idea that would consume him for more than a decade.
We call the experiment the time machine. Actually, the time machine 2, this is the second version of the experiment. We call it that because I invested 15 years of my life in this measurement. That was a lot of time. So it's a time-wasting machine, more accurately defined.
Inside this vacuum chamber are two small metal plates, sitting less than the width of a human hair apart from one another. To get them that close and not to touch, the metal has to be perfectly flat, down almost to the atomic level.
The zero-point fluctuations of free space won't fit between those plates as well. So when you bring these two plates together, there are fewer fluctuations between the plates than there are outside the plates. The force builds up, and it actually gets stronger and stronger as the plates get closer together. And that force we refer to as arising from negative energy.
The zero-point energy fluctuations outside the plates are stronger than those between. So pressure from the outside pushes them together. Or think of it another way. The negative energy between the plates expands space around it. Steve's years of meticulous labor have made him the first person on Earth to have measured a force produced by negative energy. But the amount he's detected is minuscule.
The force is equal to the weight of a red blood cell in Earth's gravitational field. So it's tiny. But if you add up thousands of these plates like we have in our experiment, you can actually achieve a palpable and useful force.
Steve's discovery may only be a baby step towards a warp drive, but he's confirmed that Miguel Alcubierre's warp drive theory does not violate the laws of physics. The energy needed to warp space and propel a warp drive forward actually exists.
So what we're doing here at Houston, we're trying to generate a microscopic instance of what could be classified as a space warp. So just to kind of give a little background, the idea of a space warp works on the principle of expanding and contracting space in such a way that allows you to go somewhere very, very quickly. When you talk about interstellar distances, it's very, very difficult to cross that distance in time periods that are not measured in centuries or millennia. So that's the idea that, or that's the limitation that drives us to think about the idea of a space warp. And, an airport has those rolling walkways that you can get onto that helps you cover the distance quicker between gates, right? So as you're walking along and say somebody's next to you walking at a similar rate, as you step onto the moving walkway, you'll appear to start moving faster relative to the other person that's not on the walkway. So in principle, that's like a terrestrial analogy for the idea of how it might appear. So it's very simplified, but just to try and help articulate the point of view. So in principle, a space warp would allow you to go to places like Alpha Centauri in time periods measured in weeks, months, as opposed to decades or centuries or millennia. What we're doing in the lab is very scientific, very controlled. We're simply trying to generate a very microscopic instance of this type of phenomena to show that we've properly interpreted the mathematics and done something in a very controlled scientific manner. So, you know, nobody needs to quit their day jobs. You're not going to bolt this to a spacecraft. This is very much in the realm of a science pursuit. But it's the right next step to take. We have to get kind of existence proof that we've properly understood and applied the mathematics. You know, general relativity has made a lot of interesting predictions over the years, so this is just one of those things where I think after a good amount of due diligence we'll eventually get there. But how long it takes to get the application, again, if it's 2 years, 20 years, or 200 years, I don't know. I think based on the work I've done in the last couple years to reduce the energy requirements to something that's a little bit more tenable. Some of the previous energy estimates were very, very large, and most scientists, myself included, were originally skeptical that you could potentially ever manifest this idea. But the work I've done the last couple of years has been really encouraging and gotten myself and a lot of other scientists interested that maybe we've moved it from the realm of impractical into plausible, and so that's why you see some of this activity at this point.